It's been a long week. I just want to go home.
So how is this grounding? So be careful. Try to figure out if you're working with perfect elastic collision or with elastic collisions, and that changes the pressure that you use. Yes.
What I tend to use these for this one because it's the
Yeah. Yeah. So you can do conservation already here, but when you try to plan out the elastic, because you have a perfect elastic collision, you will need to use those perfect elastic collision equations. These were problems from exams a couple of years ago. So these kind of problems, is the one that you can expect during for your exam. Well, you can do this kind of simplification.
Okay.
You can multiply
examine both sides of equations and then simplify. But if you eliminate something below, it has to be on full balance. So
For the first one. Multiple. So I'm using I have to put the height, so you have to do the cosine thing of like 1 minus the height over 1. You know what I'm talking about? Yeah. And then after that, I'm using the one with the conservation of energy with the potential plus kinetic equals potential plus kinetic. Additional. Like usually how PhD plus. And usually plus K plus equals usually plus K. Additional. That's where I'm at right now, and then you have to use another one after that.
this is
Find out
the adjacent side.
And then just start plugging things in to the other one.
Are you okay?
Yeah.
Are you stuck?
No, I'm waiting for you to go through it.
No. Try to do it all on yourself.
No, I have an answer.
Oh, you have an answer?
Yeah, I'm just waiting for you to do it.
It looks a little bit fine. Yeah, so double check here.
They have to. I don't know. But they're equal.
But everything else looks okay. So why don't we fix this one out?
Okay, so I'm gonna do the first part of problem 1, and then I'm gonna let you guys work on this. So you have 2 steel balls, more or less the same mass. One is 20 grams, and the other one is 100 grams. So not a big difference between the two of them. The initial velocity, we don't know. That's what we want to find out. The initial velocity of the second one is 0 meters per second. And after the collision, the second one is going to oscillate and it's going to do an angle of 50.
We can't see the paper.
Oh, we can see it better. Sorry. Give me a minute. Can you see it now?
Yes.
Okay. So it makes an angle of 50 degrees. Now, the length of the wire, that's going to be this length over here. And what we want to find out is how much gain in height do we have. So what we want to find out is this height, this delta H. Okay, so I'm going to call 0.2 the one on the bottom. 0.3 will be on the maximum deflection. And so I need to find out this delta H. So here you have a triangle rectangle. So this length is going to be 1 meter too also. And this one over here, this length over here, this is going to be 1 minus delta H. Okay, makes sense? So from this triangle, and this is 50, this is 1, and this is 1 minus delta H. So the adjacent side, so cosine of 50 is going to be equals to adjacent over hypotenuse. So this will be, the adjacent is going to be 1 over minus delta H over the hypotenuse, which is going to be 1 meter. Okay, so some of you put here sine of 50. Sine of 50 will give you this length. So just be careful with that. So from here, I can solve for delta H, and I'm going to have 1 cosine of 50 equals 1 minus delta H. Delta H will be 1 minus cosine of 50. And I think this will give you 0.36 meters. Yeah. So once you have that height, that's delta H, then you can do conservation of energy, and you can calculate what is the velocity at 0.2. So you will have conservation of energy from potential to kinetic. Okay, and I will let you guys keep work on your own. Yes.
I can't figure out which one to use for this because isn't this velocity like when they hit each other?
So because you have an inelastic collision, this will be the velocity of this one. Sorry, because it's an elastic collision. This velocity is the velocity of this guy.
The final velocity?
Yeah, the final velocity after the collision. So this will be this velocity.
I'm just thinking this. Yeah.
And you solve for the initial of
Okay.
Yeah, you cannot use this one because you are solving for the velocity that you have. You're solving for this one. But this one that you calculate here, this one is the velocity that you carrying out. So that's V2. Yes. Now, you have here, here should be 1.36. So this is the velocity of this guy after the collision. So this is much more stable. This is the velocity after the collision of this guy. You need the final velocity for this after the collision.
So when the data comes in via, mass two, instead of via, do you equal the kinetic energy? It's what the energy
No, so you have the equations for perfect elastic collisions, and you can have one equation that gives you the final velocity of mass 1. You will have another equation that gives you the final velocity of mass 2. So the final that velocity after the collision, which is what you have to. So you use.
Okay, so I got this far. I'm just not sure what equation is next.
So what does that equation, what does that speed, the velocity represent?
This initial velocity of this one.
Okay, so that's the velocity of that ball after the collision. Okay, so this is.
Oh, it's the final velocity of two, okay.
Yep.
Okay.
There you go. So you have 1 times 9. But you have the same mass.
Yeah.
The same mass, you will have but it's also 0.1.
For the initial velocity. So I took like the max of this one, and then what times that be?
This mass is the same mass.
Oh, but then the velocity is gonna be zero, so then this is all zero.
This is 0 before the collision, but after the collision, that is something different. That's what you find in here. Yeah? This velocity is the velocity after the collision.
So then you change this mass, but it's still the unknown. This velocity is the unknown.
So this velocity here, this v2, this is the velocity of the second mass after the collision. Okay, so I'm gonna be solving for that. So I'm gonna have 0.1, 100 grams, times 9.8 times 0.36. That's the height at which I start, and it's gonna gain some speed. So I'm gonna have 1/2 of 0.1 times v2 squared. So the masses are gonna cancel, and then I'm gonna have v2 squared equals 2 times 9.8 times 0.36, and then v2 will be the square root of all that. Okay, and Rihanna, no, the final velocity of ball 1, we actually don't know what is that velocity. Oops. I don't know what happened. There you go. So here I get 2.65 meters per second. Okay, you got that?
No. Like, I used the right equation and everything, but I had, like I had 1/2 0.02 v1 squared. on the right side.
Okay, on the right side.
Yeah,
On the left side, you have this.
yes, I have that on the other side, but then I divided the left side by 0.02.
So remember, right now, what we're doing is we are going to just look at how this ball, the one of the 0.1 grams, 1 kilograms, how is gaining speed as it's moving down on this pendulum motion. So right now, we're just looking at this mass over here.
Okay.
Okay, now when this velocity over here, this is the velocity after the collision. Okay, so we still need to find out what is the velocity of the small mass. Now, because this is it's a perfect elastic collision, well, for the perfect elastic collision, we have two equations. We have this one, and we have this one. Okay, those are the two equations that we have. The terms that are here, we eliminate those terms because the initial velocity of 2 is 0. The initial velocity of the big mass is 0, so these terms are going to cancel each other. So we have these two equations. Now, we need to solve the initial velocity of 1. This is what we want to find out. But this value over here, this is going to be this one. This is the velocity of the second mass after the collision. So they represent the same thing, even though we have a different variable, a different name for them, but they represent the same. This is the velocity of mass 2 after the collision. Okay. So from here, we can calculate that initial velocity. So I'm going to have m1 plus m2 over 2m1 times p2f. Here, and I get 7.97. Okay. Mary, did you get a little bit higher than that?
I did, but I got a different, I messed up earlier, but I fixed it and now I got it.
Oh, you got that one? Okay. Yeah, this makes sense, Helena? Makes sense? Alexis? Yeah. Haley? Yep. Now, with B1, we can find, with the initial velocity of 1, we can find the initial velocity of, the final velocity of 1, and we'll see that it's going to be a different velocity. It's not going to be 0. And because M1 is smaller than M2, we're going to end up with a negative initial velocity of 1. So the velocity is going to be bouncing off to the left. But just be careful. We're working with the final velocity of the larger mass before and after the collision. It gets a little complicated because how we name the different parts. Just try to keep track of those. Just so you know, when you're moving from one equation to another one, how that value gets represented in the new equation. Okay, makes sense. Any questions from this problem? Okay, makes sense in the chat? Just not. Okay. So let's do number Let's do number 3. You need to convert the miles per hour to meters per second, just so the units make sense and you can have the newtons second. Okay, just be careful. We're assuming, in this case, we're assuming an inelastic collision. Just, you want to change this to meters per second. What?
Miles per hour.
What's the case?
Okay.
Consistent?
Oh, right.
This is for perfect elastic collision. Yes, because that's perfect elastic collision. Inelastic.
I do.
I've been underliners.
I know, but in my head, I was like, yeah, that's the elastic one. So it's cruising to a thousand, so. You can look it up.
So just be careful. They're moving in the opposite directions. So one has to be negative. But it should show that equation. Like V9 is
How are you supposed to erase 2 unknown? You don't have a final velocity. There's only one final velocity in this equation. What? There's only one final velocity in this equation. There's 2. No, there's 1. Yeah, I'm sure, we agree.
Emma, what you got for part A?
I wasn't really sure if I used the right equation, but for the V1 or V1F, I got negative 22.3 meters per second.
Emma, I don't know if you answer. I mean, I can see that you have your mic open, but I didn't hear anything.
Oh, can you hear me? No.
Emma, can you hear you okay?
Is it 0? 0?
0.
Oh, okay.
Yeah. It's 0. I mean, oh. You can hear. So what did she say? I didn't hear at all. Apparently, everybody can hear what Emma is saying, but I cannot hear her. So in my mind, Emma is ignoring me. Now I'm offended. Okay, so I'm gonna go through part A. You should have got a final velocity of 0. Okay, and I'm gonna try to explain why. It seems kind of like weird result, but so you have your 2 cars. Okay, and they have the same mass. And they have pretty much the same velocity. So I think you should have got 22.3 meters per second. And for the second car, the same. But because it's traveling in the opposite direction, one is going to have a negative velocity. So, and the negative it just indicates the direction of the car. So it just means that they're going opposite direction. Now, remember that we are working with conservation of momentum. So we know that in conservation of momentum, it means that there's no change in momentum. Delta P is going to be 0, or final momentum is going to be equals to initial momentum. Okay, so the initial momentum will be the momentum of these two cars before the collision, and the final momentum will be the collision, the momentum of the cars after the collision. So the initial momentum will be the initial momentum of the first car plus the initial momentum of the second car. Okay, so this will be mass 1 times the initial velocity of 1 plus mass 2, the initial velocity of 2. So this will be 500 times 22.3 plus 500 times negative 22.3. And you can see that these two are going to give you exactly the same value. So you're going to end up with the initial momentum is going to be 0. It's not that each car doesn't have a momentum. It's that the momentum of both of them cancel each other. So the net momentum is going to be 0. So if the initial momentum is going to be 0, well, that implies that the final momentum also has to be 0, because we're working with conservation of momentum. Now, I know that the initial momentum is going to be this thing that I got here. And the final momentum, because we're working with an inelastic collision, we're going to have m1 plus m2 times the final velocity. Remember that an inelastic collision is when you have two objects colliding and they get stuck to each other. So at the end, both of them are going to have the same velocity. So the only way that the right side is going to be 0, the only possible way is if the final velocity is 0. The masses cannot be 0. You cannot have negative masses. These are not going to cancel. This factor over here is always going to be positive. So the only way that you're going to have the right side to be 0 is if the velocity is 0. The other way you can see it is, okay, you know that this side is going to be 0. So velocity is going to be 0 over m1 plus m2, and this is 0. Okay? Makes sense? So yes, you got 0. That's the right result. That's the right answer. It just doesn't make much sense. Well, it's kind of weird result. You will expect something different. It's just that you have the two cars going head to each other. They have exactly the same mass and velocity. They crash, and they just stay there. Okay? Bless you. So the change in momentum for both cars. So what is the change in momentum for car number 1, and what is the change in momentum for car number 2?
it gonna be a number or is it gonna be 0?
It's gonna be a number. And by the way, 0 is a number too.
But it's not like.
Technically,
No.
it is a number. I'm just saying. You should get the same change in momentum for both cars, just opposite value.
Did you get a change in?
Yeah.
Well, then, no. What is that? It's about where the mass is.
So
If you add them
So
together, it's
you
0,
have,
but like individually, they're just gonna like be the same number on positive, one negative.
and you have.
But like if you added them together.
Yeah.
I kind of want you to get.
No.
So this one will be the negative
11 passes.
1.
Okay, so we're at 0.
Now, what you have to do,
I got 50.
so where the,
What's the?
so everything that you have here, just. So that's the.
What'd you get for the last?
Both parties.
Like when you.
Right now, it's just based on different, because they're getting energy, they're getting it high or going down.
Let me try.
So like 2.3. 3 what? Because I used 22.35, that's why it's such a.
How's my goal loss starting?
So you will look at the energy at the beginning, before the collision, and after the collision. So before, you don't have kinetic energy, and you assume that you're not getting any height or speed or anything. So you only have kinetic energy. So you can calculate what is the energy of each car and just add it together. And after the collision, what is the energy after the collision? Because they don't have any velocity, there's no kinetic energy. You will get guessing?
Why is there no thermal energy?
What is what now?
Is there no thermal energy in this equation?
Yes, but it's not the same kind of energy that we've been calculating before.
Okay.
So if you look at your energy at the beginning, you have all of kinetic energy, and after the collision, there's no kinetic energy. Like both cars have 0 velocity. So all the kinetic energy goes to 0. So everything goes into heat, but it's not the same kind of thermal energy that we've been calculating with the friction coefficient or whatever.
Okay.
What's the equation I used them for?
Mhm.
Okay, so I got that big number.
Okay.
That's right, for one of them.
For one of them, you will have to do it again for the second one.
Okay.
Okay, so for part B, I think most of you got it correct. So we're looking at the change in momentum for each one of the cars. So the change in momentum is just the final momentum minus initial momentum. The final momentum is going to be 0 because full stop. So there's no momentum. For the first car, we're going to have m1 times the velocity, times the initial velocity. So this is going to be 500 times 22.3, and this gives you 11,000, what else?
11,150.
150 Newton second, negative. And for delta, the change in momentum for the second car is exactly the same, but here we'll have a negative. So you will have 11,150 Newton second. Okay. For part C, we have an initial energy before the collision, and we're going to have a final energy at the end of the collision. Remember, because we have an inelastic collision, there's no conservation of energy. There's going to be a lot of energy that's going to be just wasted. And you can imagine it's wasted because of the deformation of the metal or heat or something else, but it's heat that is energy that is not going to be there. So at the beginning of the collision, we're going to have, or before the collision, sorry, we're going to have 1/2 of m1, the initial velocity of 1 square, plus 1/2 of m2 times the initial velocity of 2. And the final, the energy at the end, is going to be 0 because there's no, because the final velocity is going to be 0. So there's no kinetic energy. So all this energy is going to be released. It's going to be wasted in terms of heat or thermal energy or deformation or some other kind of energy. So from here, you end up with a huge number. Eleanor, what you got?
Energy, I got 124,000.
1.25 times 10 to the 5th joules for each one of them.
Yeah.
So this is going to be close to 2.5 times 10 to the 5th joules. Okay.
Can you go through that? Like with the numbers and the
So you have the kinetic energy, the initial kinetic energy for one, and the kinetic energy of the second car. So you have 1/2 of m1 v1 initial square. I'm just doing step by step first. So this will be 1/2 of 500 times 22.3 square plus 1/2 times 500, 22.3 square.
I forgot to square it. I'm good now. I didn't square it, so that's why my number was here.
2.5 times 5 joules. Okay. Yes.
Does it matter that one of the velocities is negative?
Well, because you're squaring the quantity, so even if you have negative 22.3, because you're squaring it, it's not going to change. Now for part where we are, D. For part D, we have one car, same mass, and it's going to hit a wall. Okay, so now we know that this car is going to be at is going to be the same car, 500 kilograms, but now the velocity is going to be 100 miles per hour, which is twice what we had before, so it's going to be 44.6 meters per second. So it's going to cross the wall, and after it crosses the wall, the final velocity is going to be 0. Okay, just going to come to a full stop. So we want to know what is the release of energy. So we're going to have 1/2 of 500 times 44.6 squared. So this is going to give you, oh, where's my calculator? Oh, there it is. .97 times 10 to the 5th joules, which is almost 4 times what we got from one single car, from the energy in one car. Okay, you doubled your velocity, you quadrupled your energy. We're not going to have time to do the last one. We're going to do the last one on Friday. So Friday we'll do the number 3, and then we'll do another larger problem, and that will probably eat. Move it down. Okay, is that okay, Alexander? Okay. Any questions? Mariano, any question? Shall we go? Okay. I was just ready. She didn't even waited for the answer. It's like, I'm done. Okay, have a good day. See you guys on Friday. Thank you. Have a good day too, Elizabeth. Thank you too. Bye. Thank you. Thank you. Oh, it's stable? Yeah.
Where's your wallet? Don't lose. What? Where's your wallet? Where's my wallet?